All right, in this video, we're going to start talking about just different ways of representing functions and curves and equations, and specifically how we're going to graph these things. So we're going to start with talking about parametric equations. This is essentially just a new kind of way of thinking about and defining curves. We'll talk a little bit about how we graph these parametric curves, and then we'll just hit a couple of basics of these things. Later on, we'll go into some more examples, and we'll look at how to do calculus on some parametric stuff a little later. But in this video, we're just going to give a quick little intro to things to see how it goes. So this is basically the idea. The current kind of paradigm or viewpoint that we have is that we define some set of points on a curve by mapping a domain to a range, right? A set of x values inputs to a set of y values, and we do that with some y equals f of x function, or maybe we don't even have a function. Maybe we just have some sort of relation that connects a domain and a range, a set of inputs and a set of outputs. And then by doing that, we get a whole bunch of points, right? Whichever x values are connected with y values, that becomes a coordinate pair, and then we can go ahead and plot these things in the xy plane. We know how to do that. We like to think about how the output y changes as the input x changes. That's our idea of slope, right? So that's something that we've got. For a parametric view, though, instead of defining a function or a curve as just a collection of these kinds of points, what we do is we describe specifically the path that it takes over the course of some time parameter. So we introduce some third variable. We call it a parameter t, and we define both our x and y coordinates based on t. And so instead of our function being y equals f of x, we have two functions that tell us as time changes, where do the x values go? And as time changes, where do the y values go? And so we just have the path that's defined by the movement horizontally and the movement vertically as time changes. That's a little bit different than what we've normally done. So normally what we'll do is we'll write in our regular kind of Cartesian setup, y equals some function of x, and now we have x equals a function of t, y equals a function of t, and we have some range of time values. Normally we start counting time at 0, which makes sense. We count forward in time. Sometimes we'll have an ending point in time, sometimes not. So we can have lots of different options for this little inequality at the end. You can almost think of this as like a domain, except it's not the normal way of thinking about domain graphically, but these are just the set of time values that are reasonable to think about this path that we're taking. All right, so how do we graph one of these? It's really easy to do it in a very naive way. If you think way back to the first time you learned about graphing functions or equations or whatever, you probably set up a little table of values that were kind of like this, right? Except you would have had some inputs x and then you find the outputs y. Here, we're just going to pick a bunch of these time values, and we'll notice that these are just some of the time values, right? Time, where we're assuming, is going to be some sort of a continuous variable between 0 and 8. So there's probably a time of like 0.279 that we're not accounting for. But we can find a bunch of these points, plot them, and then try and connect the dots reasonably to get a nice smooth curve. So let's go ahead and just do a couple of these, and then I'll let you do the rest. So for t equals 0, we're just going to plug in 0 into our x function, and pretty clearly we get 1. And when we put it into the y function, we get -2. Now for t equals 1, we're going to get 3 for x, and we're going to get -1 for y. I'm going to pause it here and just let you fill out all the rest. And once you've filled them out, go ahead and plot these points. Draw a set of axes here. I'll go ahead and do that. I've got my straight lines ready to go. We've got our x and y axis, again, just like normal. So go ahead and see if you can plot this curve after you've filled all these things out. I'll pause it here and we'll pick it up in just a sec. All right, so here are all the points. This is obviously not to scale, but then once I've got these things plotted, I can try and connect the dots with a nice smooth curve. And you'll notice that, I didn't miss some, but that's okay. You'll notice that since our interval starts and ends here, we don't have that this curve keeps going. We're just going to start and stop it at these closed endpoints. So that's how we would do this one. All right, we can do the same thing here, right? We can go ahead and plug in all these t values. Now, here are a bunch of angles that I'm just picking, and this one is going to keep going because all we have is that t is greater than or equal to 0. So we're going to have to keep moving forward on here. But because of these trig functions, we're probably going to notice that there's some repetition going on, right? So I'm only going to plot a couple of these points, and then after that, we'll probably see what's going to happen with some nice repetition. So go ahead, fill out this table, plot your curve, see what happens. All right, so here's what we've got. Hopefully you can recognize what shape this is, right? I didn't plot a whole bunch of these points in the second, third, and fourth quadrant, right? We just stopped after pi over 2, counting all these angles in between, because again, we kind of know how trig functions work. They have this nice kind of periodic and symmetric behavior. So anyways, hopefully we can notice that if we connect the dots, we're going to get the same kind of movement in all these quadrants, and bang, we get this nice circular curve, which maybe we could kind of expect if we think about it for a couple minutes at what's going on with these x and y values. Doesn't this look like how we define a unit circle, except now we're scaling it out to a radius of 5, right, where the x values are the cosine and the y values are the sine values at these angles we normally think of t. But anyways, that's how that one goes. So graphing this parametric curve is not so bad. And then since it keeps going after 2 pi, we just keep going around and around and around this circle for larger and larger values of t, which makes sense. Now let's think about this for a second. We are talking about movement. We're talking about a path. We should care a little bit about direction. So let's just think about direction for a second. What we're going to do is define something called positive orientation. Positive orientation is pretty much just the direction that our curve, that we travel along our curve, I should say, as t increases. So if we go back to this first one, this shape, what we can do is just start adding in some arrows maybe, right? Because for small values of t, we started at this point on the bottom left, and we moved up this little curve up here. For this circle, you'll notice that when we started, we moved this way around our circle counterclockwise. So I'll just add in some arrows indicating what we're going to call the positive orientation. As t gets bigger, this is the way that we move. So since we're talking about traveling, every time we graph a parametric curve, we need to indicate this somehow. Sometimes you'll see people just write a little note that says, hey, you're traveling around this thing counterclockwise, but in most visuals of this, you'll see some arrows or something like that describing it. We really should care about positive orientation, we'll call that. We probably recognize these curves, right? If we go back and look at them, if you graph things a little bit cleaner than my first one especially, you might notice that that's a parabola of some sort, or at least a portion of a parabola, because we have had that starting and stopping point. So maybe we want to see, can we actually write these in a form where we would recognize that, right? Some y equals a function of x, where we can see, oh, this is a parabola because it's a quadratic function of x. And in that last one, we had a circle pretty clearly. Can we write this where we can see our normal equation of a circle? What we call this is eliminating the parameter by just getting rid of that parameter t. And there's a couple of different methods that we can do to do it. Let's just take a look at this first example. This was our parabola. There's a pretty nice way of eliminating the parameter. What we can do is just solve for t and substitute. So what I'm going to do is just solve this thing here for t, and I'm going to say if x equals 2t plus 1, then that means that x minus 1 equals 2t, and so t equals x over 2 minus half. And now that I have some representation of t, I can go ahead and substitute that right in here, and I can see pretty clearly then that y is going to equal t squared, but t is x over 2 minus half, and then we're going to do our normal subtract 2. So what we have then is that y equals, what's x over 2 minus half squared? That's going to be x squared over 4 minus a half times x over 2 times 2. So that's just going to be x over 2 plus a half squared. That's a quarter. And then we have our minus 2 again. So we can say this is x squared over 4 minus x over 2 minus a quarter minus 8 fourths, right? That's going to be negative 7 fourths. So this is really our parabola. If you want, you could also have written this in a little bit of a cleaner way, maybe factor out that quarter, and then we have x squared minus 2x minus 7 times a quarter. And so if we go up to that first picture that we had, where did it go? Here it is. That's what this parabola is. It's a portion of it, right? Because we're just cutting it off at these time markings at t equals 0 and t equals 8. But this is our normal kind of regular version curve that we would have. In this case, it's a little bit tricky to solve for t. This is our second example. We could try and do that, and we'd get something like x over 5 equals cosine t. Oops, there we go. And then we could say that means that t equals like inverse cosine of x over 5. But we should be really careful about doing stuff like this, because what you'll notice is that the inverse cosine function doesn't actually give us every single point that we might care about. You might remember from trig class that the cosine function is not one-to-one, and so when we build an inverse for it, we have to just take a portion of the cosine function. All this to say that this can be kind of tricky to solve for t if one of these functions is not one-to-one. So what we're going to do is use our intuition a little bit, and we're going to say, wait a second, I know how circles work, right? I remember how those things look. It's something like x squared and all that kind of stuff with a y squared. Let's just draw some stuff here. Let's go ahead and say, what if we looked at 5 cosine of t squared plus 5 sine of t squared? What does that look like? Well, that's 25 cosine squared t plus 25 sine squared t, which we could factor out of 25, and that's suddenly cosine squared t plus sine squared t, which is just 1 by the Pythagorean theorem. So what we've just shown then is that x squared plus y squared equals 25. Or we could say, hey, doesn't that mean x squared plus y squared equals 5 squared, right? That's our radius on this thing, just like we found. We'll leave it as 25. But that's a nice equation of a circle that we have. There are some other things that you can do here. You can use that inverse cosine function and do some substitution and some fancy trig work to do this. But if we just graph this thing and recognize that it's a circle, we should kind of know the general form of that kind of standard equation that we would have defining that curve. So these are some things that we can kind of think about as we're trying to define these things and convert back to kind of that regular y equals f of x version of this. Let's take this and run with it. Let's think of some specific types of curves that we're going to start recognizing here. Linear functions are pretty easy to notice. What we have is some, well, let me just jump right into here. We'll notice that we have some point here, x naught, y naught. That's these initial values, you can think of them. And that's literally the point that we start at when t is equal to 0, right? So this is just a starting point on our parametric curve, you could think of it. But on our line, it's just a point. And so what you'll notice then is that if you solve for t and do some kind of moving around, the same kind of stuff that we did earlier, you're going to get some sort of a slope and a point. And it fits really nicely into our point-slope form. So this is just the equation of a line. So b is the rate of change of y, and a is the rate of change of x. And so the rate of change that we normally think of, slope, is the change in y over change in x. So it's b over a in this case. Circles we've already seen, but now you'll notice we just did some fancy shifting here. We can shift our x values and y values, and that adds in these horizontal and vertical shifts, so we don't necessarily have to center our circle at the origin like we did our example. In our example, we had like 0 plus 5 cosine t and 0 plus 5 sine t. You'll also notice that there's this extra value b in here that when we go ahead and convert this over to our standard form, it doesn't show up in here because it's just a scaling thing on the inside of our sine and cosine functions. It ends up acting like a speed, and it impacts the direction that we travel. You could think of it impacting the period of the sine and cosine functions, and so it's going to impact how quickly you start repeating things. It's a speed component, essentially. Positive values of b, though, mean you're going to be moving in that counterclockwise direction. Negative values of b mean you're moving in a clockwise direction, and so they can change the positive orientation on there. So we'll just keep an eye on that kind of thing. And then you could ask the what-if question, like what if you just change the radius, the scaling factor on each of these trig functions? What if instead we did something like a times cosine of ct now and b times sine of ct, where it wasn't 5 necessarily on these? Well, what you do is you get an ellipse, right? You get this stretched version of a circle where the radius in one direction is different than the radius in the other. So that's exactly what we've got here. We have this new starting point where it's x plus a because we're shifting things around a little bit. Whatever that radius is going to be out there. And then we have y naught here for the vertical starting point. But again, we just have this scaling factor on these that's going to change the radius. It's going to stretch things a little bit. So that's all that we've got on these. There are lots of other things that we can look at here. In the next video, we're going to start taking a look at some more examples of these, but quickly we want to start moving to how to actually do calculus on these parametric curves. We're going to care about the same kind of calculus things that we've cared about already in our 2 semesters of calculus. We're going to think about things like rates of change, and we're going to think about things like areas under curves, and we'll start setting that up in this new parametric form. So that's what we've got coming up soon.